So we're looking at lesson 79, Hopitals rule. And what this is this is a rule that's going to help us find some limits of things we wouldn't be able to find without this. So sometimes we have limits that are quotients and end up being a fraction that can't be evaluated. And you see these different things here. And these are each called indeterminate forms. The reason they're indeterminate forms because by some of the general principles we've talked about, they could equal more than one thing. So just looking at this first one here, 0 divided by 0. Well, we had learned in the past that if you divide 0 by a number, you would get 0. But we also learned that dividing by 0 we can't do, it's undefined. Or we think of a number divided by itself as 1. So just looking at this one situation, it seems like we could get 3 totally different answers. And each one of these other 4 kind of are the same idea. So what we do is we have Hopitals rule, and this helps us find a limit of a quotient that if the limit ends up being in one of these indeterminate forms. And we only use Hopitals rule if it is an indeterminate form. Otherwise, we just think through it as we would before. So this says, and we have an extra apostrophe here, Hopitals rule, if the limit as x approaches a of some function f of x over g of x is an indeterminate form, and if the limit of the quotient of the derivatives exists, then those limits are actually equal to each other. And so what we'll end up doing, if we take the limit of something and get the indeterminate form, we'll go ahead and take the derivative of both the numerator and the denominator. We do that separately. We don't use the quotient rule. We just take the derivative of the numerator, derivative of the denominator, and see what that's equal to. So we'll do several examples of this. So in this first one, we have the limit as x approaches 0 of sine of x over just over x. Well, if we would think of this limit, we can put 0 in both of these. Sine of 0 is 0, and we have another 0 here. So this fraction part as the limit is 0 over 0, so it's an indeterminate form. So what we'll do is we'll take the limit as x approaches 0 of the derivative of sine of x, which is cosine of x, and the derivative of x, which is 1. And then we'll evaluate this limit. Well, the limit of cosine x as x approaches 0 is 1, so we get 1 over 1, which is just equal to 1. So although we took the limit of the first one, it was in indeterminate form, we could take the derivative of both the numerator and denominator and find that the limit is 1. Our next one, if we put 0 in here, we would get a cosine of 0 is 1, so 1 minus 1 is 0 over 0 squared, which is 0, so that's an indeterminate form. So what we'll do, same thing using the rule, limit as x approaches 0 of, and we're going to take the derivative of this, so this is negative sine, and then that's a 0 over 2x. And now we'll put 0 in here. Well, we still have an indeterminate form. This gives us negative 0, which is 0, over 2 times 0, which is 0. So we'll do it again because we found a derivative of something, a quotient. It's an indeterminate form. So let's take the derivative again. And that is negative cosine x over 2. And taking the applying the limit, we get negative 1 over 2. And so the limit of this is negative 1/2. So that's the limit of this one and the limit of this one. So negative 1/2 is our answer. Our next one, in the past we might think, okay, well let's factor this. So we don't want to forget our old things. If we factor out an x, we get an x squared minus 4. Factor an x out here, we get an x minus 2. Actually, this factors, so I'm going to cross this out. That's x plus 2 times x minus 2. And we can simplify a bunch of this. The x's cancel. X minus 2 cancels with x minus 2. And now we can actually apply this limit with no problems. We can put 0 in for x. There's just this x plus 2, and our answer is 2. So don't forget our old stuff that we learned, simplifying fractions, and not some of the other stuff. Next one, limit as x approaches 1 of natural log of x over 2 minus 2x. So if we applied the limit here, natural log of 1 is just 0. And then 2 minus 2 times 1 is 0. So what we'll do is we'll take the derivative of both of those. Derivative of natural log of x is 1 over x. Derivative of the denominator is negative 2. Now applying the limit, it does work. So we have a 1 over 1, which is 1 over negative 2. And our last example here, we actually have an x approaches infinity, so that's different. We have cosine of infinity. Well, that keeps changing. That really oscillates or changes between negative 1 and 1. That says negative 1, 2, 1. This approaches infinity, and so does this. So this really gives us an infinity plus 1, basically, is the highest to get, or negative 1 still is infinity. So we get an infinity over infinity. And so let's try out L'Hopital's rule. We'll take the limit as x approaches infinity and take the derivative of the numerator. Derivative of cosine is negative sine plus 2. And then derivative of this is 12x. Now applying our limit, this same idea as what we had up top. This is going to go between negative 1 to 1. And this is going to be 2, obviously. So our numerator is going to be somewhere between 2 minus 1, which is 1, and 2 plus 1 is 3. So somewhere between 1 and 3, but our denominator is going to be infinity. So we have a constant, or a number in the numerator. It's not really a constant, but it goes between two numbers. So something over infinity is equal to 0. And so our answer is 0 for that one. So that's a little trickier, thinking of the cosine and sine kind of oscillating between negative 1 and 1. But it is, as x approaches infinity, is not approaching infinity, it's just going between those two. And then a number, a smaller or fixed or number over infinity is 0. And that's using L'Hopital's rule.